Hi everyone. This video is going to be a little bit scattered. I'm going to be covering a few topics which aren't really related to each other, but they're all brief, so I figured I would just combine them into one video. So first we're going to be talking a little bit about the continuum hypothesis, and this is going to take us into really a very interesting side tangent. I'm not going to go into too much detail, but this is really going to require thinking a little bit about the foundations of mathematics. I'm not too knowledgeable about everything in this field, so I'm not going to go into too much detail, but I will tell you a few things that you can look into more if you are interested. So first of all, what is the continuum hypothesis? And so essentially what this is saying, we have shown so far that the cardinality of the natural numbers is smaller than the cardinality of the real numbers. And you can see the video about that to remember why. And the continuum hypothesis says, and also we called the cardinality of the natural numbers aleph null, or aleph naught, and we called the cardinality of the real numbers the cardinality of the continuum, which is also, I told you, equal to 2 to the power of aleph naught. I didn't tell you why that's coming soon. Now back to what the continuum hypothesis is. It's basically saying that there's nothing that there's no cardinality. Let's just call this cardinality aleph 1. Actually, there's aleph 1 is the smallest cardinality, which is larger than aleph naught. There's no cardinality that's larger than aleph naught and smaller than the cardinality of the continuum. So it's basically saying that after you reach the first smallest infinity, which is aleph naught, the number of the cardinality of the set of natural numbers, the next thing you can get to is the cardinality of the continuum. There's nothing in between these two. And so this is a hypothesis, meaning it hasn't been proven to be true. And in fact, it's been shown that it's impossible to prove that this is true. It's also been shown that it's impossible to prove that it's not true. So when I say that it's impossible to prove or not prove, you may wonder, how can we prove that it's impossible to prove, and how can we prove that it's impossible to not prove? And this is where we touch on the foundations of mathematics. So modern day mathematics is largely built on a basis of set theory, and we've been talking quite a bit about sets and some components of set theory in this video series, but there's a lot more that you can look into with regards to set theory. And specifically, there's a set of axioms with regard to set theory called the Zermelo-Fraenkel axioms, or ZF. And sometimes there's also added the axiom of choice, in which case they're referred to as the ZFC axioms. So you can also look those up to see. And so axioms in general are statements that you assume to be true, that you just explicitly say these are true, and then you can build off of them. So everything else in mathematics is built off of these axioms. And you can work with other mathematical systems that use different axioms or something like that, but this is what standard mathematics utilizes. And so these are axioms related to set theory, and everything else can be built off of that. And so then, when we see that the continuum hypothesis has been shown to be unprovable as either true or false, this relates to Gödel's incompleteness theorem, well, specifically his first incompleteness theorem, I believe. And this was a very powerful proof and very profound, which essentially says that under any mathematical system and the axioms that hold in that system, there will be things that are true but which are impossible to prove. So that's why it means that it's incomplete. It would be complete if you could prove everything that's true, and there are no complete mathematical systems based on this theorem. And so that's also something that you might want to look into if you're interested in this. The continuum hypothesis is a super interesting concept, and I highly recommend you read up on that and maybe check out some other videos on that. One in particular was recently made by Veritasium. I think it was called something like There's a Hole at the Bottom of Mathematics, or something like that. I don't remember exactly. But that's all I'm going to say about the continuum hypothesis. Next, I'm going to talk about power sets. And I've also already mentioned them, but I'm just going to give you a quick example of what it is, so that we can use it in a future video. So let's consider a set. Let's call it A, and let's say that it has the elements 1, 2, and 3. I'm actually taking this example exactly from another video, so I can also recommend that video to you. It was made by Vsauce. I believe this was also from How to Count Past Infinity, which I've already recommended. But again, if you haven't watched it, go and watch Vsauce's How to Count Past Infinity. Great video. So now we're going to look at the power set of A, which is denoted with a curly P and then the set inside. So if you want to take the power set of any set, you write it like this, power set, and then you put the symbol that you use to represent set inside the parentheses. So the power set of A is also going to be a set, but what are the elements here? So the power set is the set of all subsets of A, and that may not be clear, but here I'll show you exactly what it is. So the first element, one subset of A, is the empty set, because the empty set is a subset of every set, actually, because to create a subset, you just pick any of the elements that you had in the original set, any number of them, and you can choose to pick none of them, and that gives you the empty set. So that means, since it is a subset of A, it belongs in the power set of A. It's one element in the power set of A. Then we can think of other subsets of A. One would be you could just choose 1, you could just choose 2, you could just choose 3. So those are also elements of the power set. And then you could also choose 2 numbers. So you could choose 1 and 2. You could choose 1 and 3. You can choose 2 and 3. And then there's one more possibility, which is you could choose all of the elements, and it's still considered a subset. So actually, let me just make sure that since there are so many subsets, so again, the elements of the power set are themselves sets. So just to distinguish, I'm going to use a different color for the outer braces, so that it's clear that this is the set. Everything inside the blue braces is the power set of A, and all of the elements of A are themselves sets, which are subsets of A. And so now we can think about the cardinality of the power set of A. I don't know if I know how to prove this, but clearly the cardinality of A is 3. There are 3 elements. Then we can count the cardinality of the power set of A in this particular case, which is 1, 2, 3, 4, 5, 6, 7, 8. So the power set of A has a cardinality of 8. Let's just write it. And so in this particular case, you can see that 2 raised to the cardinality of A, so 2 raised to the 3rd power. So 2 raised to the cardinality of A equals 2 to the 3rd power equals 8, and that's equal to the cardinality of the power set of A. So again, I don't know if I even know how to prove this myself, but this is true in general, that 2 to the power of the cardinality of a set is equal to the cardinality of the power set of that set. I know the terminology here can start to be a little fuzzy, but I hope that's clear. So yeah, that's an introduction to power sets, which I will use in a future video. But now, one more thing to talk about is transitivity. And I think, like, intuitively this is going to be very obvious, but we can show it a little more clearly. So we can suppose that you know that a set A has the same cardinality as a set B, and you also know that set B has the same cardinality as a set C. So the way you might have proved this is you showed a bijective function from the set A to the set B, and you also showed a bijective function from the set B to the set C. And transitivity just means that this also indicates that the cardinality of A is equal to the cardinality of C. And this seems very obvious, but it's worth making it clear when we're talking about infinities, because sometimes even intuitive things do fall through and turn out not to be true when we're talking about infinity. And we can kind of show this pretty clearly. So we can, again, go back to arrow diagrams for showing functions. So let's take a look at the set A. Let's have that over here, and then a set B here, and a set C over here. And I can only draw a finite number of elements, but you can imagine that the same argument will work even if you have infinite elements. So I'll just draw 3 in each of these, because they are supposed to have the same cardinality. So essentially, we have, since the cardinality of A is equal to the cardinality of B, that's known. That means that there is some function which is bijective from A to B. And so we can say this is a function f. It also means that we can say, and so the other one is that the cardinality of B is equal to the cardinality of C. And so this means that there's a bijective function from the elements of B to the elements of C. And so we can call this G. And so now, how can we know that these cardinalities are the same, A and C? We can create a new function, which is the composition of these existing functions. So we can say, let me use a different color again. So over here, the bijective function was f of x. And over here, the bijective function was g of x. So yeah, that meant like f of x took a value x from the set A, and it gives you a value in set B, and this is a bijective function. And the same is true with g of x, except x is this time in B, and then gives you a value in C. So now we can try and come up with some new function. So we want to show that there's a bijective function from A to C, and that'll show these cardinalities are the same. And we can do this by, like I said, composing functions. So we have that g of x is an element in C, because if x is in B, then g of x is a bijective function which takes you to C. So let's just write an element of, well, actually, let's not quite do that yet. Let's first look at f of x. So if x is in A, then f of x is in B. So let's just write a generic element in B as f of x. So this is a generic element in B. In this case, x was a generic element in B, and g of x was in C. So now f of x is also a generic element in B, so we can treat this the same as we are treating x over here. And then if you put g outside, then this will take something in B as an input, and g of something in B gives you something in C. That is the whole point of the function g, as you can see here. So now looking at what this gives you, so x in this case is going to be in A, then f of x is going to be in B, as these arrows show, and then you're going to apply the function g to this whole thing. So you're applying g to something in B, and that takes you to C. So composition of functions is enough is going to be itself, this whole thing is a bijective function from A to C. So that shows that there is a bijective function from A to C, just from knowing that that the cardinalities of A and B are the same, and that B and C are the same. So that proves transitivity of cardinalities being equal, and yeah, that'll also be useful in a future video. So yeah, this is a kind of assorted set of topics, but I hope you found it all interesting, and I'll see you in the next video. Thanks for watching.